Okay, so first I want to thank the organizers for inviting me for this workshop. And my plan is to talk about the dark machines initiative. And then also I am going to talk about some of the works that have been doing since this start. Basically, the goal of dark machines is to exploit recent advances in machine learning to help with the search for dark matter. Okay. Who is in the dark machines community? In principle, the idea here is not only to have physicists, but also data scientists and put together the knowledges. And then what the dark machines does, basically, we have been organizing several workshops since 2018. The idea was to organize once per year. And then right now we have about 300 members which are subscribed to the initiative. And the idea of this initiative is not just to have workshops and to discuss, to have talks and things like that. So the idea here is just to decide or to define which are called challenges. So challenges are, we basically identify a problem which can be related more or less related with our matter, and then this problem we try to, or we think that can be benefit from the use of machine learning techniques. And then we put together, or we try to put together physicists and data scientists to solve it. And the goal is just to get a publication. Okay. So since we start, there are several projects or challenges that we discuss, starting from 2018 till nowadays. And this has been the four that basically have worked out. There is another one that Brian told me today that already also started in some of these meetings, and they already published with mine. But these are the ones that I was basically involved on those. And then you can see, the variety is wide. So it's not just dark matter. It can be just exploring high-dimensional parameter spaces using some optimization algorithms. Can be also unsupervised collateral searches to find new physics at LHC. Or we have been working in some more astroparticle related, like for instance, try to find point sources in Fermi-like data, or discuss the possibility of put a kind of database of libraries which have been trained, and then the community can use them. Okay, so I am going to try to at least try to talk about all of them. The first one I want to talk is about the model-independent event classification for the Large Hadron Collider. This is the list of people involved, and as you can see, we have got what is the idea, the spirit of dark machines, okay, which is try to involve many people. In this case, experimentalists from LS experiments, and also some data scientists and theorists, and then kind of create a hackathon, okay, and then from this hackathon to try to publish it. Okay, the goal of this particular challenge is just to perform kind of model agnostic searches. That's why it's called unsupervised compared to the typical supervised methods. And then this is in line of what people in Atlas, for instance, have been doing, which is, these are the typical two approaches to find new physics in a very systematic way. So you have, all the possible final states that you expect or you get from the collisions. And then you look systematically one by one and try to see if there is an essence. Okay, and there are hundreds of these channels, and then you can do this basically kind of manually. Then another approach is just try to find bumps, okay, in the data. The two approaches, and then why not to use machine learning to do the same thing, okay, and do this event by event, not trying to look for bumps, but just taking an event and say and try to answer the question. Is this event a standard model or is this event any physics related? So in this case, compared to what people typically do in colliders, the whole thing comes with what is called the anomaly score, which is the output of your machine learning algorithm. And with this, you decide if the event is an anomaly event or it's not an anomaly. And with this, you can define a kind of signal regions, which is what people typically do with putting cuts on kinematical variables of particles, etc. So the first thing to start doing this kind of things, as you know, in machine learning is to generate data. And this is, in this case, is a kind of challenge. Okay, why? Because you want to do some realistic thing with which means, for instance, nowadays, with 13 TB to go to, I don't know, tens of investment dollars, you have to generate order of billion events of standard model events for what we want to do here, okay? Which is what we train. So we did this, okay? To have an idea of what we did, is just we generate about 150 terabytes of data. So we stored all the event history of the data, and then because this is impossible to work out with those, what we did just we took the essential, let's say, ingredients of the events, which is basically the weight of the event, which is the cross-section of the event, and then the objects of the event produced, which are jets, leptons, photons, etc. And then with the corresponding form vectors. So this is going to be our data. Okay. So then, in order to make things which are comparable to what experiments do, we just create 4 different channels, which are related with what you expect in terms of new physics at the LAC, that I am going to talk later. And then we also generate ESM signals, so new physics signals. It's a kind of wide variety of that, and so on and so forth. And then the idea was to train, all these models for the 4 different channels. Okay, and then we train using just standard model. This is a different thing compared to what is supervised, because in supervised you do a classification, and then what you do is just you put in to train at the same level somehow in a balanced data set. You put a standard model and BSM, and then you train just to do a binary classification. In our case, just we train on just standard model, okay? And then you expect that something which is not a standard model will be detected. So you are agnostic, okay? Because you don't know what is new physics compared to another approach that you train on something that you expect. Okay, is this SUSY, or is this, I don't know, electro-ward, or whatever. And then the next step is once you train all these models, you select the ones which are best, okay? And then you apply to a blinded secret data set that just one person knows in the hackathon. So you cannot cheat on what you are going to get. So you train your data, and then let's apply it, and then you send the results to this person, and then she basically process the data. So this is, to get an idea of what we produce. So these are the typical standard model backgrounds with the cross sections and with the number of events. So we stop to achieve the 10 investment of R. And then the pipeline to produce the data is the typical one. So you have the matrix elements part, the parameterization, and the detector simulation. And then you produce, all these jets that you observe. These are jets, jets, electrons, muons, and photons. Okay. So the cuts, as I said, we wanted to mimic what Atlas experiments basically do. So we basically create, things which are similar to what Trigger does, or something which is focused on finding jets, for instance, or something which is focused on things like finding electric gas particles with couplings, which is connected with our matter, for instance, with wind, etc., etc. Okay, so we train over all these channels. So in terms of the signals, we have this number of signals, okay, which are simplified models, so very simple topology. So you produce a particle, can be a gluino in supersymmetry, and this particle decays, just one step decay to a neutralino. Okay, the neutralino in our particle conservation, as you know, can be a dark matter particle, so it's stable and has a large vicinity. But also you can have R parity violation stuff, in which the LSP, the latest supersymmetric particle, decays in the detector. Okay, so you observe something different, or you can have resonance. All this kind of thing. So I think this mimics very well what you expect in terms of new physics atoms. And then we apply the channel, the cuts, to produce the different channels. And in some cases, you can see that there is just one signal that survives just on one of these channels. Okay. So now the methods. So because it's a hackathon and there were a lot of people involved, so we try to apply kind of state-of-the-art methods. We can classify, give you an idea about what they are about. I think you have heard about these things. For instance, the most popular thing that we apply are based on what is called autoencoders, and there are all kinds of autoencoders. Okay, we have the plain or vanilla autoencoder, or we have the variational autoencoder, or we have something which we put a convolutional autoencoder, or even more fancy things like combining an autoencoder with the normalizing flow. And there are several families of normalizing flows. Okay, each of these algorithms has their own hyperparameters, so you can just optimized on those hyperparameters. And you can see here the number of models that people train. We have something like it's an autoencoder, but in the latent space, you do clustering, okay? So this is one type. There are other types like this related with just flow-based likelihoods, which is the thing that I mentioned before. So you have latent spaces, and we want to basically infer the density of the embeddings in the latent space. Okay, and from that we try to reconstruct it. And this is the score that we get after the reconstruction. And then we have just standalone models. This is very nice thing because in this particular one, what you do, you basically infer the likelihood of your background. So if you give this algorithm, once it learns the likelihood of the background, an event, it tells you what is the likelihood or the probability that this event is background or is not background. Okay, and then we have other things like this STPD, which will repeat, will appear later, which is one of the winners of this thing, and it's a very simple thing, which is just you have it's a compressor, so it's just an encoder. So you have an input, which is the event. You have a network, which is a very simple one, even just with one hidden layer, a few neurons, and then you have as an output some embedding, which is kind of lower dimensional representation in a manifold, and then you want to basically to fold this, okay, and then you put a target number to this output, to this number, to this embedding, and then you want to reconstruct it. Okay, for that you put imagine that you have an input which is a 20-dimensional event, and then the output you put, I don't know, you want to encode it to a vector of 5 dimensions. Okay, and this vector you assign just one number. Okay, for instance, if it's 3-dimensional, you have you can put 0, 0, and 0. Okay, and then you want to reconstruct to force the encoder to reconstruct this number. And this is super simple, but it's super powerful, and I will show you later. And then there are other fancy things like clustering or density estimation, and okay, and also just for completeness, we have one which is based on cards, okay, which is called adversarial anomaly detection. There are still other super fancy things which are based on graphs, but we didn't use for okay, which have been used for top tagging, for LSE Olympics, and all that. So how we compare the model? So what we do, just we train each, the data assigned to each channel, to the background data, okay, and then this is the training data set. We have then a validation data set or test data set, which is we take some of the background events and then we add signal events, okay, and then we try to evaluate this anomaly score, which is what we use to decide if the model is standard model or not. And then for the hackathon set, of course, we know the two levels of this test data set, and then we can compute the typical, metrics, which is the ROC curve. And then specifically, we use, as typically is done in classification, what is the area under this curve, which is called the E of C. Okay, and then we also define these scores here, which are also very typical or familiar in experimental physics, which is basically what is the signal efficiency using some background efficiency, which is fixed. What is the meaning of this? The meaning of this is that this is the signal efficiency, which is how good is your classifier to detect any physics, and then this is putting a cut on the background. Okay, so this is a kind of loosey cut, and this is a kind of tight cut. So it's you try to remove background, okay, with these numbers, and then you see, or you want to see what is the signal which is left, okay, which is something similar to what experiments do typically. And then the point is how we present all these results, okay? And then the idea that we have was to use this kind of plot in which we have the metrics on the x-axis, we have the method, and then we have two things. One is just we have all these signals, okay, in different colors, and then we put just one over the other, okay? But then what else we can do? We can even try to do some summary statistics, because we can have this summary box and whisker plot in which we just taking these numbers here and we compute some mean, some mean, and then some quartiles, etc. And then basically this contains the whole information that we want to decide what is best or what is not best. So at the end of the day, we get this kind of plots. Okay, so in this case, four panels. We plot on the x-axis the metrics. We plot on the y-axis the signals, and we plot in different colors the different channels. And then this is quite, there are a lot of information here, but there are two things that I want to say. First of all, is that there are some BSM models which are very easy to detect. In this case, you see that all the metrics are maximized, okay, to 1 for ruinos and for stops, okay, which is kind of expected because what you produce here is high PT jets, okay, compared to the standard model of high vicinity, okay. Then there are models which are very challenging that related with electroweak production. Why? Again, because you can see these are masses of charginos, masses of neutralinos, which are not very far away from the mass scale of the standard model, no particles. So you expect that the masses, the particles or the jets that you produce are not very high PT, so very similar to what's produced in the standard model. And then you have something which is mixed, which basically works, in one channel, but doesn't work in another. But still, this is quite a lot, no? And then it's very difficult to say what is better in terms of performance. So how we can continue, compressing information. And to do that, what we did is using the definition of what is the signal efficiency and the background efficiency that I mentioned before. We define what is called the significant improvement, okay, which is kind of the factor that to add, to your typical significance of a signal. No? Because what you have is the significance is typically the signal over the ratio of the background, but when you apply the cuts, you put a factor on the signal on the background. So it's S prime divided by B prime because you applied some cuts. Okay, so this represents this factor that you put in front, which is coming from the cuts that you apply. So then what we can do just because we have these three numbers for the different cuts on the background efficiency, just we maximize over there, and then just we reduce to just one number, which is this number that put here, which is the maximum significant improvement. Okay, if you see here, still it's very difficult to assess anything about if this is better or not. You can have a general idea, but not what we wanted. So what we did is define this, this based on this total improvement, which is the, is defined as the physics signal as the maximum, improvement of background and of regions of the channels of interest. And then what we did is define these quantities, the mean PI, which is basically a score on the hardest signal. Okay, we have the max PI, which is the score on the easiest signal. And then we have the score on the medium signal. Okay, and then we plot correlations here. And then with these correlations, we can see what we expect in terms of performance. And this is what happens. These are basically all the methods that we apply, okay, in different textures. And then you can, for instance, we can see here that there are models that have a very low score on the easiest signal, which is something that we don't want, okay? And there are a lot of those. But there are models who have top scores on the hardest signal because they have a larger mean TI, okay? That basically is a kind of a score on the hardest signal. And then, so we identify already the one that I told you before, the SDTT, which is a very simple model. Is not, there are no flow, there are not this super sophisticated stuff, just a simple network. And then even you can get even better things, maximize the max TI and the mean TI and the mean and the median TI, sorry, and then which are these ones here. And this is the likelihood-based model that I mentioned before, okay? And then a kind of combined that I am going to talk to later of the flow model and the STD, how we combine the scores that you can do that in order to maximize. So now we have a more clean idea of what we can get in terms of the ranking. So then what we have to do, another selection. Okay, so we put a cut on the median TI larger than 2, and then if you do that, we select these models here. Okay, and then of course we can just continue keeping these ones in order for checking, etc. So I skip this one and I go to the final one, which is this. So now we want to compare. Okay, we train our models. We score basically. We rank the models at the level of the Hatacon data set, which is just training data and testing data. And then now we want to see how they perform with the secret data set. Okay, so I plot one against another, and I plot the median TI because it's the quantity which is let's say less bias compared to the mean and the max. And then we put a cut on 2, okay, on both. Okay, and then we are left with a very few models. These models are these ones, okay? So these are the best ones because they are quite optimal for both data sets, for the hackathon and for the secret data. And these ones are very much related with this SVTD, which is a very simple network, and with the standard beta variational autoencoder, which is a variational autoencoder. I guess you know something about variational autoencoders, that you have your loss function, have two pieces. One is a mean square error, which is typically what you use to do reconstruction. And you have something which is related to the Hubel-Leiber divergence, okay? And then you put a beta factor in front of this time. And then with that, you drop the mean square error, okay? So your loss function is just the Hubel-Leiber divergence for this case. Okay, so very simple models are the best for this. Okay, how much time do you have? Okay, so this is another thing that we did, which is completely orthogonal. Sorry about that, it's too much information. Which is trying to do a detection of point sources in the gamma ray sky. Okay, using kind of U-shaped convolutional networks. Okay, the motivation for this project is just the idea that the idea to detect point sources in the sky, which is correlated, with astrophysics, because they are typically astrophysical objects. But then on top, can be objects which are more kind of exotics, like coming from dark matter, with some dark matter halos, and it's quite a challenge to do these kind of things. And why is a challenge? Because typically the background is completely, is not understood completely. So there are different models of backgrounds. It's quite bright in the center of the galactic plane, so it's very hard to detect anything there. And then once you detect something in one length, you have to assess that you detect it also in another wavelength. Okay, and then this is not easy because they use completely different, hardware, so different devices, etc., etc. Okay, so in the literature there are some attempts to this, not using just raw lab images, just using the catalogs, and then there have been also some attempts using just radio data, and people developed some software for deep source. Okay, that works very well based on deep learning. So our goal here is just repeat this with deep learning, classify sources. Okay, so detect, localize, and classify sources using lab sky images. Okay, the pros is that deep learning, we know it's a powerful tool, completely, computer vision. So it's very easy to generalize to other wavelengths, as has been done in radio, for instance. And then the cons is that you have to create the training data. Okay, and this is not very easy actually. And then you don't use any test statistics to decide if there is a point source or not, as is done typically by the Fermi-Lab collaboration. The work that we did is not using real data; it's a kind of proof of principle project. Okay, so just to let you know about what we want here. So we have the gamma sky. Okay, as you can see that the galactic plane is quite bright due to the backgrounds. And then what the lab collaboration do is just basically perform some statistical analysis based on likelihood. Okay, and then they just collect points or patches here, and then just do some test statistics and likelihood ratio, and then to estimate if there is a point source or not. And then for that, they put a cut on 4 sigma detection. Okay, see if there is a possible candidate for a point source. As far as I know, there are about 2,000 point sources which are detected, and I think 1/3 of those are unidentified or unassociated. Okay, so it's not clear that there are point sources. So what we want to do is just replace this test statistics that they use with machine learning using computer vision. Okay, so we take this as input, the image, and then we just want to take one patch of the image arbitrary and say how many, I mean, there are point sources, where they are the point sources, what kind of point sources they are there. Okay, and for that we need to do the generation of the data. And this is the trickiest part of the whole thing. And then for that, of course, you use some reference, which is the Fermilab catalog, okay, the most recent one, where they put the detected point sources with the coordinates, the properties, etc., etc. So this is the guide that we use. And then we generate basically 3 types of populations on point sources. One, which is the F0, which basically mimics what the 4FGL tells, okay, as you can see, but we extend it to lower values because we want to go beyond the response detection of the Fermilab. And then we add another 2, which are F1, which is just flat, you can see here, and we go below order of 10 to the minus 4 in the units, the luminosity function, and then we have F2, which is not flat, and follow some okay. And then on top, we have to generate the point sources we decide to be pulsars, or which are basically in the galaxy, or AGNs, which are extragalactic. Okay. For generating this is, again, there are a lot of physics because you have some spectral information that you take from the catalog. You have to put in some positions that in some cases is just kind of random. In other cases, they have to have some distribution. Okay, and then on top, you have to generate the backgrounds. Okay, and the backgrounds, there are uncertainties. So you can play with different background models. So we generate 3 different background models. The problem with the backgrounds is that you have the gas in the galaxy, you have these cosmic rays around, they have interactions with the gas and they produce these gammas. And also there is some magnetic field which is not completely known. So depending on how is the distribution of the gas, you can have different models. Okay, so we wanted also to play with this and to see how performs the algorithm to change the background models and it would change the population. Okay, and then of course with these ingredients we can generate maps with photons. Okay, using some tools which are part from the collaboration. So we generate the photon maps, which are these kind of maps. Okay, so it's a full sky map, and then we generate 1,000 of these. Okay, but because you cannot train on this because there are thousands, I don't know, in galactic coordinates, maybe there is 1,000 times 1,000 pixels. There's 1 million pixels, you can train this kind of thing. So what we did, we trained just patches. So we just split it in patches, and the patches, have, basically 10 times 10, degrees, okay, which basically is about 65 pixels times 65. And then we take 5 energy bits. Okay, that's typically done. And then for classification, we just detect the point source, we put a square, which is just 1 degree times 1 degree, which is about 7 pixels times 7 pixels. Okay, this kind of arbitrary. Okay, as I said, this is a proof of concept. And then how we go to the machine learning part. How we want to detect the point sources. So the input is just this kind of image. Okay. Something that I had to tell you is that when we generate the photons, it's a kind of Asimov data set. And then what we have to do is to add noise in terms of the Poisson noise. And then what you get is this kind of very noisy images. Okay. So we have 64 times 64 times 5. Okay. And then what you want to do with that? You want to do kind of segmentation, which is what you typically do in computer vision. So segmentation is that for each pixel, you have to assign a class. In this case, there are 2 classes: point source or background. Okay, and then you want to find a model, a network model, which basically correlates this input with this one. Okay, so we use 2 different technologies, which are based essentially in the same thing, which is the unit. The unit in our case is the one that do the cementation. And then once you do the cementation, you can imagine that in some cases there are points here, point sources which are apparently detected, but they are very close to each other, but we don't know if they are physical or not. So we have to do a second step, which is a kind of localization, and we do this using two algorithms. One is kind of clustering algorithms that maybe you have heard about, what they means, and then you have something which is called majority voting. There are 2 algorithms. They have a common thing, which is a unit. I am going to talk about later. And this is more sophisticated because in this one, we not only do cementation, we also want to predict each pixel has a vector which points. This is kind of abstract, okay? It's difficult to get it, but each pixel of the image, okay, points to a centroid corresponding to an object, okay? So we do also regression in this. And then what we do at the end of the day to know if there is a point source or not in some specific place is just we count, okay, the vectors that point to a specific pixel. And we take the centroids are the ones who have more poles or more vectors pointing to that. Okay? So there are the two things, and then you get something like this. Okay, now the ingredients in terms of machine learning. So the main ingredient is the unit. What is the unit? I think you have heard about that. The unit is a kind of architecture, which is a kind of bottleneck. It was developed in 2015, and it was a breakthrough in the field. It was used for biomedicine at that time. Nowadays, it has been used for everything, I think. And the point here is that, okay, you have an input image, you have the segmented one, okay? So you do the mapping, but you do in the following way. You have kind of compressed your data or your input somehow to a lower resolution, okay? But in here you learn high features, okay? And then you just do upsampling, okay, to collect the same resolution that before. But if you do that, probably you lose, the localization thing. You learn what is what here, but you don't know, or you don't learn what is there, okay, or where is that. And then for that, what they do they have something which is called residual connections. So the residual connections just basically combine high level features at low resolution with low level features at high resolution. And this basically gives a very good result. What else we do? Once we detect something, we basically try to classify that. How to classify something in an image with the convolutional network. And then in this case, what we do, we have two classes, as we had before, the AGNs and the PSRs. But then on top, we define something we call the fakes. Why the fakes? The fakes is because sometimes there are false positives that you detect with your algorithm, but they are not point sources. Okay? The algorithm is not good enough to detect that, and then detect something which is, doesn't have any match with the true source. And then we put this like another class. Okay? So the results are really cool, as you can see here, because for instance, if you take high latitude where the background is less bright, so it's more easy to detect something. So you see, this is the input image, kind of. You see, super noisy. You have in process the two point sources, okay, that we put some squares on that. And then we see that the network detects false positives. These are not existing, but they are detected. These are our fakes, okay? And there are some also false negatives that are there, but they are not. But the point is that in the classification, all of them are well classified, even the fakes, if you take a cutoff of 50%. But what happens if you go to low latitude, when the background is very bright? In that case, you expect a worse performance. In this case, we have no. In this case, we had AGNs. Now we have quasars and AGNs, and then still, detects a lot of the real true point sources. There are something which are just false positives, false negatives, and then in this case, it's different because now you can see these which are marked here, which are misclassified. So they say here, for instance, like this a true PSR, but instead it's a false positive. Okay, so this is just to give you an idea of how this works. Also, you can just do other things like you can try to assess the sensitivity to the detection to the different backgrounds or to the different machine learning models, and then for that you basically define this is just the flux over some energy. In this case, it's 1 GB, and then you put kind of cutoff or threshold to see that your detection is good, okay, calibrated somehow, and then you say that your in this case your detector is good if for fluxes which are above values which give a completeness larger than 0.9. Okay, and then this is the completeness definition, and then also you can even go further and then try to compare with other results in the literature. And then in this case, we do the same thing. Instead to integrate the flux over 1 GB, we integrate over 10 GB. And then this is basically the restful detection in terms of the completeness, because it's otherwise it's about 0.9, okay? And then this is something that has been explored using the different technique in the literature from the Mauro et al. In 2018, and you see that we can be better than that, okay, about 20%. But this is not a fair comparison because we have not used the same amount of data. They use, I think, 7 years of data. We use 9.5 years of data. And this is the summary for this. Okay, so we with these methods, okay, we can construct a very good, machine learning model to do, segmentation, detection, localize, and classify gamma rainfall sources. Then it can be connected, for instance, with exotic physics like dark matter. The results are very comparable with what Fermilab does with a very manual, and artisanal method. It's very robust to changing the background model. In terms of classification, it's really good because it can go up 70% of accuracy. It passes an AGN, and they are the public repository for the software and for the data. Then to finalize, I want to talk a little bit about, if I have 5 minutes, for the optimization algorithms, okay, for particle and astroparticle physics. So again, this was a challenge that was, discussed in 2018. Okay, and there are two parts of this. We have to start with the first part, which is just optimization. Why optimization? We as physicists, we typically use optimization when we do basically inference based on likelihoods. But what we want to do here is just minimize the likelihood function. Okay? So it's an optimization problem. And it's a very typical about the astroparticle physics and particle physics, right? So in practice, at the end, in what I know more, which is about particle physics, for instance, if you take a realistic model that could be supersymmetry, okay, and you take, I don't know, you have to know about the MSSM, which has 100 parameters that you can just reduce to 20 parameters, and then you can still reduce more with some assumptions. And in this case, for instance, the people of Gambit collaboration, they took this model, they did a global fit of this model, and then this model, to do the global fit, you have to do, for instance, LHC full Monte Carlo simulations. Okay, so you can imagine how expensive is this. And then at the end of the day, you get something like this. Okay, you get regions which are highly more probable. You have degeneracies, okay, because there are 2 islands here, you can see, that are a good fit to the kind of good fit, relative good fit to the results. And then in this case, it's a real challenge to do this, okay, because it's the likelihood that you want to minimize. It's very complex. In this case, actually, it's even not continuous, okay, because there are many points in this parameter space which are just not physical, so you cannot assess any number to the likelihood because there is no likelihood. And then on top, there are the likelihoods are multimodal. Okay, there are many points in this parameter space where you can satisfy all the constraints, like dark matter, etc. So the sampling is super complicated. Okay, so you basically never know if you are settled down at the end of the day in the truth, in the truth. And this means, or this needs to do, I don't know, millions or even billions of likelihood evaluations, including LHC events production. Okay, so the idea was to try to also again to do a kind of ranking in terms of algorithms, which are state of the art for optimization. And then the critical point here is that we don't use gradients for this, because as I said before, not all the problems, you can use gradients. For instance, for the case of particle physics, okay, in the MSSM, because the likelihood is not continuous. So we just took, popular, let's say, algorithms, which rank from just a normal random sampling to a Gaussian particle filter, which is a kind of random sampling, but some priors. Then you have the typical differential evolutionary algorithms, artificial bee colony, which is based on how the bees work in real life. And then we want to try to get a universal matrix, okay, to run all of them. And then for doing that, we take kind of choice samples, which are based on functions, which are analytical. So we know what are the true minima. And then we also play with the dimensions. So we go from 2 to 7 dimensions. And then on top, we put a realistic case, which is the MSSM, like, okay? So these are the functions, which as you can see in 2D, they are super nasty, especially this one. This one has just very, very narrow, very sharp pitch, okay? So maybe in 2 dimensions, okay, maybe you can get something, but if you increase the dimensions, you can start seeing that no of the algorithms, these algorithms work at all, okay? Then you have other functions who have a lot of minima, and they just have one global minima. You have others who have, a lot of minima, but they are equally all of them. So it's a complex problem, like the Xbox, like Christoph was mentioning before. And then you have something which is similar to this one, but there is a clear global minima, and still there are a lot of local minima. So we do the test in 2 up 7 dimensions. And again, the thing which is very important here is that the true minima was known only for one person in the challenge. And then these functions were provided in a binary format. So you cannot know what are the true minima. So you cannot cheat, okay? So you take your algorithm, and then just you do the optimization, and then just you compare to give the results to one person that knows that, and then process the results and create this kind of plots, okay? And these plots are very, very informative and very concise because, okay, each of them, they have a different function, 1, 2, 3, and 4. And then we plot here, basically the true minima normalized to the minima that these algorithms get normalized to the true minima. On the y-axis, you get the different algorithms that I mentioned before. And then in terms of plotting, we put, dots, okay, cycles. For the different dimensions are represented with different color, and then the size is represented by the number of the calls to the function that you need to convert. Okay, so all the information that you need is basically here. And from this you can get a few conclusions. Okay, the first one is for function number 1, which is this super nasty with a sharp peak. There are just one of these algorithms, the ABC, the artificial deep learning one, that work best because it's able to get the minima, okay, the true minima. There are others that they are able, but just in 2 dimensions. Of course, when we increase the number of dimensions, you see that no one basically works. Okay. So what happens with function number 2, which is less nasty? So in that case, there are a lot of algorithms in the list that are able to get the minima, but at different costs. Okay, because some of them they can get it very quickly. That, for instance, the differential evolution, or this one here, which is the work optimization thing, and the other ones they get it, but they need a lot of evaluations, which basically we don't want. No, when the evaluation of the function that you want to get is very expensive. For function 3, is very similar. Okay, there are a lot of algorithms that work in all dimensions, okay, from 2 to 7. But then there is one just that converts faster, okay? And then the function number 4, again, there are a lot of algorithms that work, but there is one which is the differential evolution, which is faster. And then this is what we get. And then we pass to the MSSM7. The MSSM7 is just a model. We have some parameters, okay, which are parameters that we want to do inference, and then there are others which are nuisance parameters, which are parameters that we know from the standard model of astrophysics, standard model of particle physics, masses and couplings, etc., etc. So at the end of the day, it's a 4-dimensional field. Okay. So this is super expensive, as I said. So for each of these algorithms, we cannot run all this optimization because it's very costly to do the lazy simulations. And then what we did is we just tried to parameterize in a deep neural network, which is a fully connected network. And then for doing that, to learn this, we use about 10 million likelihoods, okay, from the data set that this collaboration provides, or the analysis they do. And then we get that we learn, or we got a network that learns very well, the correlation between the input, which are these parameters, and the output, which is the log likelihood, which is the cost function that we want to. And in this case, the situation is really bad. Why? Because as you can see here, we plot again. In this case, in the x-axis, we plot the log likelihood, the true one, versus the one that the algorithm gets, and then we see that just one of the algorithms get to the right path, okay, to the mean. And what is the thing here is that, of course, to get these points that I use for, or we use for training, we have to use some optimization algorithm, and that optimization algorithm was exactly that. So we were kind of cheating somehow with this algorithm, but it's something that you cannot afford at all because you have to use something. Right? And then the other algorithms, you see that they perform very, very well. This is a kind of summary table to kind of say something or take a decision about what you want to use or not. But according to this table, from my point of view, in terms of let's say accuracy in determining the true global minima and the number of evaluations, for me, this artificial bee colony is one of the best. The diver, which is differential evolution, I think is at the same level. And then the others, they have some characteristics that, maybe they are good in something, but they are bad in other things. So it's really kind of model dependent, okay, in this case. So there is all this software has been folded in this GitHub, so people can take it and play with it, okay? And then just to finish, I want to mention something about something that we discussed in the short 2019, which is why to provide a library of training models to the community. Okay, why we wanted to do that, especially for the Pheno community, because typically everything that we do when we do phenomenology implies very expensive calculations. So even just compute cross sections, in some cases, and next to leading order, for instance, is very expensive. So the plan was to provide some networks already trained that people just can take it, okay, and use it as they are. And then we start discussing some applications, and then we start with just networks for just producing electrical production cross sections in models like the MSSN, which is something that people in Atlas or CMS do. They do these kind of things, and next to in order, and it's very expensive to do it. Then loop integrals for doing NLO calculations, or just big global fields, as I mentioned before, or even just to do reconstruction of efficiencies of lonely particles. So something that, instead to have a table, which is a kind of 2D or 3D table, and to do a simple interpolation, is something that you can just promote to higher dimensional, and then you do a more sophisticated interpolation with a network. This is what basically that. Okay, then just to end up, just again, Dark Machine is what it is. There is a web page, there is a Twitter, and then people can subscribe to that. So last year, the 2020, the workshop was canceled. And then this year, because the pandemic again, but we plan to maybe next year have again the meeting at CERN. And okay, and the idea will be to basically discuss about new challenges for that is the idea. And that's all.
Is there any question?